Hi, I'm Philip Paul. Thank you for viewing this demonstration of my self-driving car simulator. I'm a long-time software developer who is retraining to become a self-driving car software engineer. I would like to accomplish 4 objectives with this presentation. First, share a bit of my personal background and how I came to make this career change. Second, provide a high-level view of the self-driving car architecture that I used as the guide for the simulator. Third, overview the primary features that I implemented in the simulator. And fourth, show the virtual car driving on several maps to demonstrate the ability of the simulator. I've always loved writing software. I taught myself to program at age 11. I earned a degree in computer science from the University of Michigan. For most of my career, I was the owner, operator, and basically the sole programmer of a hosted case management and reporting system. My software was used by more than 70 social service agencies in 12 states and supported more than 500,000 clients. Over the years, I grew the product to more than 80,000 lines of code and generated more than $11 million in revenue. I was inspired to become a self-driving car engineer after watching a documentary on the 2005 DARPA Grand Challenge. The Grand Challenge was the first long-distance competition for driverless cars. The competition was extremely intense and exciting for the students and engineers who participated. I thought it would be really cool to join a top-level team that was working to bring this type of technology to consumers. I'm currently enrolled in the Udacity.com Self-Driving Car Engineer Nano Degree program. I've completed about 340 hours of coursework and have about 800 hours of coursework to go. After my first few classes, I decided to build a scale model self-driving car to reinforce the fundamentals I had learned so far. I discovered that Google engineers test their algorithms in the software simulator before running them on public roads. I decided to break my project into 2 phases. In the first phase, I built this simulator, which allowed me to work through much of the software design for my scale model car. In the next phase, I'll build the physical robot using the simulator as its software framework. I used Udacity's self-driving car architecture as the guide for my project. Udacity has 5 major systems in their architecture. Computer vision allows the vehicle to perceive the physical objects in its vicinity through the use of sensor devices such as cameras, radars, and lidars. Sensor fusion classifies data captured by sensors into information called features that are actionable by the vehicle. This includes determining the distance, shape, trajectory, and speed of the objects around the vehicle, such as street signs, pedestrians, and other vehicles. Localization uses systems such as GPS in combination with the vehicle's sensors to determine where the vehicle is in the world and where it is on a particular road. Path planning provides instruction to the vehicle as to where it should go and what it should do to deal with the objects it encounters along the way. Vehicle control replaces the human driver by controlling the vehicle's driving systems, such as its throttle, steering, and brakes. The design goal for my simulator was a self-driving car that could drive through a virtual world using standard driving conventions. While driving, the car would have to successfully navigate common road artifacts, including adhering to signs and traffic lights, and avoiding moving objects such as pedestrians and slow-moving vehicles. I wrote the simulator around 4 primary systems. The map maker allows the user to define maps, which include roads and road artifacts, which are the objects that appear on and around roads. The object class is the foundation class for all the visual objects that can appear on a map, including the roads, road artifacts, and the car itself. The object class provides methods for placing, moving, and managing proximity among objects in a map. The sensor class simulates physical sensors and provides information to the car about its environment. Classifier class objects simulate the processing of sensor data and provide the classification, location, and instructions that allow the car to deal with the objects it encounters on roads. The administrator is the main processing unit of the simulator. It includes the route planner, which provides instructions that drive the car along the roads and through the intersections of a map. It also continuously pings the car and interrupts the route planner when the car's sensors return instructions necessary to accommodate road artifacts. Although I will write the software for my actual scale model car in C++ or mostly in C++, I wrote the simulator in Pygame using the Pygame library. The simulator is a little more than 1,500 lines of code. To demo this simulator, I'd like to show how maps are configured, how the car drives through a map, how the car interacts with road artifacts, and finally show the car driving a complex map that demonstrates all its capabilities. The map maker allows roads and the artifacts that appear on roads to be configured. The roads of a map can have any number of lanes, though all roads in a map have the same number of lanes. Roads themselves have two attributes, direction and length. Here are some example roads. A 1 kilometer single lane northbound road, a 1 kilometer 2-lane southbound road. Between any two roads, the map maker adds an intersection. Here are two 1 kilometer 3-lane westbound roads connected by an intersection. Perpendicular roads are connected by an intersection that results in a turn. Here is a westbound road connected to a southbound road. In this example, the simulator's route planner is driving the virtual car in a map with 13 configured roads. When the car enters a road, the route planner builds a series of virtual waypoints called a drive guide that it uses to steer the car to the end of the road. The simulator displays the drive guide as a series of red dots. For straight roads, the route planner produces waypoints along a straight line. For turns, the route planner produces waypoints along a circle arc that connects the two perpendicular roads. The only control the route planner has over the car itself is the car's heading. It steers the car by successively setting the car's heading to the closest waypoint in the drive guide that is in front of the car. Whenever the car is off its intended path, the route planner displays a green heading indicator, which makes it easier to see the car calibrating to the drive guide. In real-world self-driving cars, objects that appear on or near the road are first observed by sensors. Classifiers process the sensor data into features the car uses to accommodate and avoid colliding with the objects. A real-world self-driving car classifies hundreds of objects. I built a virtual sensor into the simulator that classifies 6 road artifacts that are organized in 2 categories: stationary road artifacts and moving road artifacts. The stationary road artifacts are speed limit signs, stop signs, traffic lights, and the destination indicator. These road artifacts help the car navigate roads. The moving road artifacts are pedestrians and slow-moving vehicles. These road artifacts share the road with the car and are objects the car must avoid colliding with. Next are examples of the virtual car classifying each of the road artifacts. In this map, the first road contains a 45 speed limit road artifact. The classifier for this artifact sets the car's speed to 45. The second road contains a 65 speed limit road artifact. When the car approaches this artifact, its classifier sets the car's speed to 65. For any road that doesn't have a speed limit road artifact, the car drives at its most recently set speed. The artifact at the end of the third road is the destination artifact. The destination road artifacts classifier sets the car's throttle to 0 for several seconds and then informs the simulator to launch the next defined map or to relaunch the current map if no other maps are defined. In this map, the first road contains a stop sign road artifact and the second road contains 2 stop sign road artifacts. The classifier for this artifact sets the car's throttle to 0 for several seconds. You'll notice that the car sometimes becomes surrounded by a red border. This indicates that the car is responding to instructions from a classifier. In this map, the first and second roads contain a traffic light road artifact. The traffic light road artifact cycles between green and red traffic signals. When the car approaches this road artifact, its classifier sets the car's throttle to 0 whenever the signal is red. In this map, both the first and second roads contain 2 pedestrian road artifacts. The pedestrian road artifact simulates a person crossing the road in the middle of traffic. In the real world, cars stop to avoid hitting people who are in the road, and people stop to avoid stepping into oncoming traffic. I designed a collision buffer system to imitate this reality in the simulator. The classifier for the pedestrian road artifact stops the car whenever it encounters a pedestrian in its collision buffer. You'll notice that the classifier shows the collision buffer in yellow whenever it stops the car. Similarly, I built a collision buffer into the pedestrian road artifact itself that prevents pedestrians from walking into cars. This map is configured with 1-lane roads where both the second and third roads contain slow-moving vehicle road artifacts. These artifacts cycle through slowly driving the length of the road they are placed on. The classifier for this artifact causes the virtual car to match the slower car's speed when the virtual car reaches a specific distance behind the slower vehicle. For brief moments after the slow-moving vehicles reach the end of the road, you will notice the virtual car returning to the posted speed of 65. This map is configured with two-lane roads that contain slow-moving vehicles. On multi-lane roads, when the virtual car approaches a slow-moving vehicle, the classifier for the slow-moving vehicle looks for an adjoining lane. If it finds an adjoining lane, it builds a drive guide that it uses to pass the slow-moving vehicle rather than slow down behind it. The drive guide for the lane transfer combines two circle arcs to facilitate the merge. One arc steers the car to the center point between the lanes, and a second arc steers the car to the center of the adjoining lane. Once the car reaches its target in the adjoining lane, the route planner regains control, builds a driving guide for the new lane, and steers the car to the end of the road. This map shows all three types of moving object interacting with each other. In addition to two slow-moving vehicles, I've added a few pedestrians. You can see that the slow-moving vehicles have the same collision avoidance capability as pedestrians, and that all of the objects sense and avoid running into each other. This final map puts it all together and shows the full capability of the simulator. The map includes the 4 road directions, the 8 possible turns, and at least one instance of each road artifact. I'd like to point out one segment of the drive that especially highlights the simulator's administrator. The administrator includes the route planner, which senses roads and provides instructions that allow the car to drive along the roads. It also gathers and prioritizes instructions from the car's classifiers that allow the car to handle the road artifacts. Take a look at the long eastbound road at the top of the map. While the route planner is driving the car in the left lane, the car's sensors identify a slow-moving vehicle. The slow-moving vehicles classifier sends the administrator a plan to move the car to the right lane. The administrator interrupts its driving in the left lane to begin executing the lane change. However, while attempting the lane change, the car's sensor identifies a pedestrian in its path, which causes the pedestrian classifier to instruct the administrator to stop the car until the pedestrian passes. Once the pedestrian is clear, the administrator completes the lane change plan and finally receives and begins executing a new plan from the route planner that finishes the drive on the road in the right lane. Even though the administrator is a single-thread application, it seamlessly prioritizes the instructions from the car and its classifiers and safely drives the car even through unexpected compound interactions with multiple road artifacts. My goal with this simulator was to make a comprehensive exploration of the software necessary to power autonomous vehicles. I believe the experiment was successful and that my simulator will be sufficient to power the scale model robot that I will build in the next phase of the project. Thanks for taking a look at my demo, and I'd appreciate any feedback or suggestions that come to mind.